Hi, Assalamualaikum. Today we will present our group project about stroke prediction is novel agenda rented Abdul Talib, and these are our members.
Age is one of the most important factors in determining an individual's health status, risk of chronic disease, and overall physical condition. As people grow older, various psychological changes occur in the body, including metabolic changes and will influence weight status and body composition. Body mass index, which reflects an individual's weight relative to height, is frequently used as an indicator of obesity and general health. Understanding whether BMI has a relationship with age is important, as weight pattern and body composition often change across different stages of life. Some individuals may experience weight gain with age due to lower physical activity, slower metabolism, or lifestyle factors, while others may experience weight loss due to aging-related health changes. This study used a stroke-related dataset but focused specifically on analyzing the relationship between age as the dependent variable and body mass index as the independent variable. Through descriptive statistics, correlation analysis, and simple linear regression, this study aims to determine whether BMI can help explain variations in age within the given dataset. So the objectives of this project are to describe the descriptive statistics of BMI and age. Number 2, to identify the strength and correlation between body mass index and age. Number 3, to model the body mass index and age using simple linear regression. And number 4, to make a prediction using the simple linear regression model. This study is significant as it helps provide a clearer understanding of how body weight status, represented by BMI, may relate to age variation within a 5/60 population. Since age is closely linked to psychological and metabolic changes, examining its relationship with BMI allows researchers to identify patterns that may reflect important health trends. Understanding this relationship is useful in interpreting whether individuals with higher or lower BMI tend to fall within certain age range. Such insights may contribute to recognizing potential health risks, lifestyle influence, and age-related metabolic adjustment that people commonly experience throughout different stages of life. In addition, the findings from this study support future research in public health, epidemiology, and nutrition by highlighting the importance of monitoring BMI as part of overall health assessment. The study encouraged better awareness of weight management and how it may relate to age-related changes. Overall, this study provides valuable information that can contribute to improving health strategies, guiding further investigation, and promoting healthier practice across different age groups.
Hi, my name is Nofar Shafika Muhammad Fazli, and today I would like to talk about Chapter 2, Methodology. This methodology can be divided to three parts, which is 2.1, Data Description, 2.2, Graphical Techniques, and lastly 2.3, Numerical Technique. 2.1, Data Description. I would like to talk about type of data, type of variable, and the level of measurements. The two types of data is age, the type of variables, independent, which is a natural predictor that progresses steadily over time and is not influenced by other variables in the model. The level of measurement is ratio, which is any measurements including magnitude, equal interval, and absolute zero. Next, body mass index (BMI). The type variable is dependence. It represents the health outcome and may change in response to age. The level of measurements, the same as age, which is ratio. Any of measurements including magnitude, equal interval, and absolute zero. 2.2 Graphical Techniques. Histogram. Our group chose histogram this because histogram is an ideal graphical tool of visualizing continuous numerical data. Data is measured on interval or ratio scale. Continuous variables can take on a wide range values, including decimals. Age and body mass index (BMI) are examples of continuous data. Next, 2.3 Numerical Techniques. Under the titles of descriptive statistic analysis, first means. This is the formula, which is sum f multiply xm over n's. Means the meanings of mean is the average of the observation and frequency distribution. From the formula, sum f multiply xm, which is the sum of the products of the frequency f and the midpoint xm for each class, and the total frequency of the data. 2. Medians, which is the point at which 50% of the case fall above and 50% of the case fall below, or we can also say that it's a middle value in data. The formula that we use is L plus N over 2 minus CF over F multiply H. The meaning of L is lower boundary of median class, and total frequency, N over 2 half of total frequency, CF cumulative frequency before the median class, and lastly F frequency of median class. Number 3, minimum, the lowest value found in our chosen data, and number 4, maximum, the highest value found in our chosen data. Next, number 5, standard deviation, which is the measure of dispersion to measure how dispersed the data is in relation to the mean, while variation is the square value of the standard deviation that show how spread of the data is. These are the formula that our group use, which is S equal to square root sum f x minus x bar power of 2 over n. The f is the frequency of each class interval, x the class midpoint, x bar the mean for group data, and lastly n the total number of observation. Next, numerical techniques under correlation and regression analysis. First, present correlation coefficients. The meaning of this is measure the strength and duration of the linear relationship between two numerical variables. This is the formula that our group chose. Firstly, it can be interpreted into four: R below zero, positive relationship; R above zero, negative relationship; modulus R approximately 1, strong relationship; and modulus R over 0.3, weak relationship. Second, coefficient of determination, which is statistical measurement that examine how difference in one variable can be explained by the difference in a second variable when predicting the outcome of given events. And lastly, number third, simple linear regression model. We use y equal to a plus bx. Y is predicted value, which is BMI, x predicted variable, age, and b slope.
Hi, I am Aisha and I will explain about Chapter 3, the result and the interpretation. So for 3.1 is data presentation. This is the histogram of the age with the body mass index BMI. Show that the histogram is positively skewed to the right. The age is independent variable while the BMI is dependent variable.
Next, for 3.2 is descriptive statistic analysis. From the data, these are the data of body mass index with age that has been collected to get the descriptive statistic. Okay. From the table, we can see that sample size of BMI and age is same, 150. The mean for BMI is 27.27 and the age is 55.41. However, the median of BMI is 27.71 and the age is 57.5. The minimum of BMI is 15.24 and the age is 19. The maximum of BMI is 39.43 and the age is 90. The last but not least, the standard deviation of BMI is 6.69 and the age is 90.92. So, I will explain about regression statistic. The multiple R is equal to 0.1138. There is a weak positive correlation between age and BMI. Next is R squared. R squared is equal to 0.0129. The meaning is 1.29% of the total variation in charge is explained by age, while another 98.01% of the variation is explained by another factor. Next is the slope. The slope is equal to 0.0382. The meaning is for every 1 year's increase in age, the BMI is expected to increase by 0.0382 units on average. Next, the intercept of coefficient is 25.1542, while the intercept for standard error is 1.6139. However, the coefficient of age is 0.0381, while the standard error of age is 0.0274.
So for the all report summary is this study was carried out to examine the relationship between age as the dependent variable and body mass index as the independent variable using a stroke-related dataset. The analysis began with descriptive statistic, which provided a clear overview of the distribution, central tendency, and variability of both age and BMI in dataset. This initial step allowed the identification of important characteristics such as the average age of respondents, the typical BMI range, and how widely the data points were spread. The correlation analysis was then conducted to measure the strength and direction of the linear relationship between BMI and age. This analysis helped determine whether the increase in BMI were associated with increase or decrease in age, or whether the relationship was weak. Identifying this relationship is useful as it provides preliminary insight into how body weight status might align with age patterns within the sample. Following this, a simple linear regression model was developed to further assess the nature of the relationship between the two variables. The model produced a regression equation that explains how changes in BMI may influence or predict changes in age. This regression equation also enables the generation of age prediction based on specific BMI values. The significance of the slope was evaluated to determine whether BMI provide meaningful information about variation in age. Overall, this study successfully achieved all the objectives outlined in Chapter 1. It described the descriptive statistics of both Z variables, identify the direction and strength of their relationship, construct a regression model, and demonstrated how the model can be used for prediction. The findings contribute to a broader understanding of how BMI may relate to age variation and provide a foundation for future studies in health, aging, and metabolic research.